Here are the units as per definition of cleanliness. They are conventionally people use this particular. There are many parallel definitions, but this is more often used: class, 100,000, 10,000, 1,000, 100, 10, and 1. So as you go up the ladder here in the pyramid, the room becomes cleaner and cleaner, and also the conditions also become stringent and more stringent. So the room here right now is way below here. Actually, it's much more dusty than what is listed out here. So you can see, even if you claim that you have a class of say 10,000, in that you will have particles which are measuring 100 nanometer per cubic feet. You will have 100,000 particles there. And if you're talking about around a micron type of particle, you have around 10,000 particles per cubic feet. So still large number of dust particles are still there, but it is almost serving the practical purpose. So if you're standing here, you can carry out device fabrication at least for academic purpose. Class 1000, class 100. I'm not sure whether Professor Fisher would agree with me. They are having a very major facility, Burke Nanotech clean room, where I think the cleanliness is maintained at 100 and above. Am I right?
10 and 1.
10 and 1, you see that? Very stringent, right? So you can imagine how you have to be driving away the air and bring in fresh air all the time, which is filtered. Of course, you need air conditioning, you need humidity control, you need variety of things have to be done in the clean room. And even people who are working there will have to be wearing, special clothing and, eye cover and whatnot. So that's about clean room units and definitions. In fact, clean room fabrication is expensive because of all these peripherals which come about. And that's what it is when you want to make micro device or nano device. Yeah, some more photographs showing. In fact, in India there are two popular sites for academic institutions. One in Indian Institute of Science, the other one is in IIT Bombay, right? The Nanoelectronics Group. They are offering service to various researchers in various places. So you can log on to the website and register yourself and take a booking, and you can go and do the measurements there or even do fabrication there in the clean room. And in my institution, Jawaharlal Nehru Center for Advanced Scientific Research, we have just come up with a clean room again. It's also open to anybody. You can approach, you can write to me and get to use it. We have, of course, limited facilities, not the way they have in IISc or IIT Bombay. So let's go to lithography conventional tools. If I'm using photolithography, I would end up with a pattern like this. This pattern is interdigitated pattern of gold fingers. You can see these are all gold fingers, and the width of the gold finger here is 50 micron. The gap is around 50 micron. My contact pad is here, which is outside the screen. So I would take a contact from this pad, and I would take another contact from this pad. So essentially the fingers are coming pretty close. 50 micron is the only gap, and that you're going to fill up with some active material. What is that active material? It could be some supercap active material. So you're making energy device, a 2D supercapacitor. You can actually code it in this region, and these two will be your electrodes. All right. So you can plan out what you want to do with such electrodes. So this is most commonly used by very many people for general purpose electrode making. There are very specialty techniques in the literature. There's an interesting article in Nature Materials way back in 2008, how to take photolithography to its best in terms of creating 2D patterns like this. Look at these curved patterns on the surface, and they're actually having some good height in terms of the aspect ratio of the feature. They're coming up in terms of few microns, and that is also possible with photolithography. And 3D patterning like this is also a possibility. So people have specialized photolithography in many ways. I'm just talking to you the basic aspect today. So let me take you through the recipe for photolithography. We will not be able to really get into every step of it, but let's get a flavor of what it is all about when you practice lithography in general, but these slides are mostly for photolithography. So you prepare the surface, clean it up, and you bring in the resist, spin coat it, and bake it once so it will become a tight film. And then you bring the alignment using a mask aligner, put a mask and expose it to light, and then develop it. So you will have now exposed regions, whether to stay or go away in the solvent, depends on what kind of resist you are using. And further on you want to make it a bit more tight, you can have the post baking on the resist, and then you may want to bring in a separate active material on top. Finally you do the stripping and post process cleaning and whatnot. So if I tell you like this, and if you have not done this, gone through this recipe, you can hardly make out what's going on, right? So we'll actually do one given example. For example, if you take a wafer and put it on the vacuum check, you cannot be using some adhesive and all that, right? It will mess up the further steps. So you just put it on a vacuum check. Vacuum check holds it on the spinner, and then you spin it at a given speed. These are all optimization steps, okay? Depending on the resist and the process, you have to go on optimizing. And rotating at a given speed, you spin coat the resist, which decides its thickness. There's good modeling available in the literature. There are given equations in order to achieve a given thickness of the resist. What should be the concentration of the solution, what should be the spin speed, whatnot. Everything is well defined. You can also do the optimization in the lab. And you can achieve resist thickness of the order of 1 to 2 micron on smooth surfaces of silicon wafer or glass. Okay, that's not too difficult. Having done that, you see here, let's go through this carefully. This is a substrate wafer. It could be glass or silicon. And you have the photoresist, which is now here in pink or red, and this is the mask. So you have the light coming through. In this case, this is shown as UV, and light is blocked by this opaque layer parts, right? You want light only to get into these regions, and as the light falls on the resist, this region is undergoing chemical change, okay? Because this is a photoresist layer. This is what you spin coated to begin with. And then you do the development step, putting it in a solvent for a given amount of time, and then develop it. You end up with patterns here wherever the light was exposed, if it is to begin with a negative photoresist, or you actually take away the patterns where the light got exposed, I mean the layer got exposed, only the other regions remain here which were unexposed if you're starting with positive photoresist. The reason is simple. If you are using negative photoresist, you are increasing in, the polymers respond differently to light beams, okay? A given polymer may have increased cross-linking when you are exposing a beam. Increased cross-linking means its solubility in a given solvent decreases because the effective molecular mass increases, right? So it will stay on, and that's called negative photoresist. At times you will have polymers which actually break up in the light beam, particularly UV light, and when they break up, they become easily solubilizable in a given solvent, and then you can just wash them away. So the unexposed regions stay on. So it's up to you which one you want to take and go further, okay? So both negative and positive photoresists are available commercially. And these are details of the mask aligner. In fact, you are now wanting to bring the mask on a given region. Probably you have already done one level of patterning. You want to bring in the second pattern in a given orientation, in a given spacing and all. So you need very fine control, and all that is done with this kind of mechanical check. And you want to bring in the mask itself pretty close to the resist, but not touching it. If you touch, then it can pick up the resist film itself, right? You want to bring it pretty close, so you don't want the light to diverge out of the mask, right? You want to hit it straight. You want to hit the light beam straight on the substrate. So you bring it pretty close at a distance of maybe a few microns and hold it suspended and then get it exposed, right? Exposures are typically few seconds to few minutes. So let us start with, I'm now taking you through the details because these will become relevant as we go on. You can see this is the photoresist. This is a thin film of the desired material of which you want to end up in terms of making patterns, right? So let us say we want to make gold patterns on glass, okay? So what is shown here, green, is gold film on glass. And you are now bringing in a photoresist, and you have done the exposure part, what I just talked about. You have done the developing. So you end up with having resist in regions here, right? And now you can etch away the gold film. If you put another chemical which etches away the gold, you can see that only in these regions gold got etched away because these regions are masked, covered by the resist itself. And resist doesn't respond to the etching solution what you're using for gold. Finally, you can just dissolve away the remaining photoresist. You end up with gold patterns like that, right? This is one way of doing. The other way of doing is exactly the opposite, wherein you have initially the photoresist itself pattern on a plain glass. Having done that, now you bring in gold on top. You can see gold is getting coated here as well as directly on the glass itself. And then you swell the photoresist with a little bit of, you can put it in the solvent where the photoresist can dissolve. You can see that the metal is being now lifted out. And then only in these regions where it got to see the substrate, it stays on. The rest of the regions, along with the photoresist, metal also goes away during the development step. So that's how you make metal patterns. Now I talked about the possible resolution limits of photolithography, and that's all because of this diffraction equation what is shown here. These are very, we've gone through it during college time, and you can see the lambda is sitting here. If you make the wavelength of light smaller and smaller, you will have your R coming down, means you will be able to make finer and finer feature, right? You have a lot of these diffraction issues there. You can actually take the lambda down to deep UV or extreme UV, or even down to X-ray lithography. X-ray is troublesome because you need good optics to deal with X-ray, so it's not commonly used, but UV photolithography is very commonly used. Nonetheless, with all this improvement in terms of shortening the wavelength of light, you still will have smearing, broadening, all sorts of issues with light, and so they are not really used for anything below half a micron feature size. Okay, there are literature reports, research articles written even down to 30 nanometer by photolithography, but industrially, as far as I am aware, it's not used for nanoscale writing as much as other techniques are used. Now we will move to electron beam lithography techniques. Because of the resolution issues, though you can have broad light beam, right? It's less expensive to have a light beam, right? And so you can do large area patterning with fine features, but the feature size itself is limited to around a micron. So one has to shift to another type of light, another type of beam, which doesn't necessarily go through the kind of diffraction difficulties what optical field goes through, and that's what is electron beam lithography. The recipe steps remain more or less similar, so the schematics also hold good here, except that you're using photoresist, you are using the resists, these are called E-beam resists. Here also you can have positive resist and negative resist, but they are a different class of polymers, that's all. Typically people use PMMA or polystyrene. Polystyrene is a negative photoresist, PMMA is positive photoresist. As is shown clearly here, electrons can actually cut the chains, so the effective mass of the exposed region comes down in the positive photoresist, while in negative photoresist it can stitch and make it a heavier mass. So the mass stays on after electron beam exposure. And the system looks like this, is typically hooked on to scanning electron beam, scanning electron microscope. So you can do the microscopy, and with the same scanning beam you can also do lithography, right? So it's usually with SEM, and you can see some typical patterns written here, right? So those are the, people normally mention what is the beam energy and the probe current and how much is the exposure in terms of seconds. You can see there, it's all of the order of microsecond or nanosecond exposure. Electron beam is moving pretty fast, and a given location the exposure time is pretty small. But how much you can move the electron beam, you know, in terms of the axis area, it will be small only, not too big. So far we dealt with systems where we know how to bring in gold film and pattern it, right? And so what do you do with gold film? You may define some basic electrode system, right? If you want to pattern an active material with very complex stoichiometry, for example, look at this. This is a result from 2008, is an effort to make a non-volatile random access memory, and you can look at the device configuration here. This was done with electron beam lithography, okay, using n number of steps. You see here, this is a crossbar. These are all the crossbars. As you can see, these wires are platinum wires which are arranged in a crossbar geometry, and in between they have trapped quantum dots of TiO2 and TiO2 minus X. Okay, 2 minus X means it's oxygen deficient. So that junction itself provides the device functionality in terms of storing charge. And so very intricate patterns people have realized using electron beam lithography, but a very tedious process. It involves dozens of recipe steps. So I'm now moving on to leaving the conventional tools but going on to more recent innovations? Can we move away from these conventional methods? Because even doing one single material pattern, like say a gold film or something, you are dealing with at least a dozen steps. And now think of the device what I just showed you, it will involve probably more than 100 steps. So can we reduce the number of steps? Because as you walk through the 100 steps, even one tiny error may get magnified. Somewhere it will derail you, you will not end up with the kind of device what you want. And so the throughput will be much less. So people are on the lookout to reduce the number of steps and trying to achieve nano patterning much more, in I shouldn't say easy, but much more direct way. And I must talk to you about 2-3 minutes on this soft lithography method. This is one of the direct patterning methods. You can see here, in this case, you would take, you would first of all create a stamp. Stamps are typically made up of an elastomer. And these are like rubber only, just that it allows you to do fine patterning. PDMS actually allows you to do patterning even down to 1 nanometer. It can accept patterns of that kind. So if you have a silicon master wherein the initial pattern is created either by optical lithography or by electron beam lithography, then you can pick it up on an elastomer. All that you have to do is make a solution. There are commercially available elastomers available, and that solution, if you just spin coat or drop coat and allow it to cure, probably you just have to put it in an oven for